Arc length. Section 8.1 on arc length. Arc length is a shorthand way of saying the length of a curve. Any curve, and a curve doesn't necessarily have to curve, it could be straight. For example, y equals x plus 2. With something like this. Maybe I want to know how long this curve is between x equals 1 and x equals 4. So maybe I want to know how long this piece is right here. Should use another color. So I might want to know how long that is. I claim that you could probably answer that one. How long is that little piece of this curve between 1 and 4? 3? I think it's a little longer than 3. 3.5? Is that an estimate? You're just guessing?
3.25?
3.25?
Yeah,
How are you getting that?
I know.
You don't know?
Just guessing.
Well, how far is it from here to here? That distance is 3, right?
Yeah, 4.
From 1 to 4, this distance is 3. I wonder what this distance is. My picture's not to scale.
What's the y value?
Yeah, what's the y value, he says. So this point right here is 1 comma, what? What's the y value? 1, 3, I'm gonna plug it into here. And this one over here has a x value of 4, so that's 4, 6. Plug it into my equation. So how high is this one?
2.
2? 3?
3.
So we have a vote? 3. We all agree it's 3. I told you my picture's not to scale. It's 3, right? Going from 3 up to 6. This one's also 3. Now that I have this beautiful right triangle there, can you tell me how long that piece of the curve is?
9.
9?
Yeah.
That doesn't look like it's 9.
Square.
How are we going to find it? Pythagorean Theorem, right? 3 squared plus 3 squared, let's call it c to be creative, equals c squared. So that's 9 plus 9, that's 18 equals c squared. The exact answer is 3 square root of 2. The decimal answer, approximation, someone have a calculator handy?
4.24.
4.24? Thank you. Around 4.24. That's how long that curve is. So I claim that you knew how to find arc length way back when it was a straight line. Are there any other curves that you know how to find the length of? Any other graphs that you know besides straight lines? Circles. So here's the top half of the circle. Maybe it's x squared plus y squared equals 25. And maybe I want to know just the length of this piece right here. I know that piece. Did you find that length? I got a couple nods. Not as many as the line. It's a circle. Yes?
Didn't we already do a problem like that?
Maybe we might have.
In an earlier section.
We might have been finding the area in the earlier section. I think you're right. I think we did do one where we took a portion of the area of the circle. But now I don't want to know the area. I just want to know how long is this piece. If I could stretch it out and make it straight, how long is this piece right here? What do we know about this circle?
That's 4 quadrants.
It's in 4 quadrants. Okay. What else do we know about this circle?
It's a fourth of the circumference.
Ah, so this piece right here, she says, is 1/4 of the circumference. You agree with that? The circle goes all the way around. Hopefully, most of us remember how the circumference of a circle. Hopefully. Don't all say it at once. Circumference of a circle is 2 pi r. Do we know r in this circle?
Yes.
Yeah, what's r? 5? X squared plus y squared equals r squared. So the circumference in this case is 2 times pi times 5, that's 10 pi. So that little red piece right there is 10 pi over 4. I'll call it L for length. Which we could reduce to 5 pi over 2. And we could turn it into a decimal if we wanted to. What'd you say?
Oh, I called it 2.5 pi.
That's the same, I agree with that. 2.5 pi is the same as 5 pi over 2. I don't know any other curves that I can find the length of without using calculus. These are the only ones I know, lines and circles. But what if it's a parabola? What if it's a sine curve? What if it's an e to the x curve? That's where 8.1 comes in, the arc length. What we're going to do is derive a formula with calculus that will help us find the length of any curve as long as you know your function. As long as you know your function, even if it's e to the x. So even if I come along and I graph something that looks like this, y equals e to the x, and I want to know how far is it from 1 to 4 on this guy, I can find it. That's the goal. What's up? You got a question, Chad?
I was going to ask if I need to use this for labs.
Mm-hmm. You can. Everyone okay on the idea? Okay, so if you look at your notes for 8.1, what page are we on?
63.
63? It's pretty much blank except for the pictures. So what we're going to do is derive the formula that helps us find the arc length. So this is the first picture that you have over on your left. So what if our curve looks like that and you want to find the length of it? The idea is that we're going to break it up into shorter pieces. Maybe from here to here. This might not match yours exactly, but you get the idea. Smaller pieces, points that are on the curve. And then we're going to connect some straight lines going between those. This is a straight line here, a straight line here, straight line here. Now, if I add up all these straight lines, it's not going to give me the exact length of the curve. There's kind of missing part of it, right? But do you agree that if I put more points on there, it'd be closer to the actual length? And the more points I put on there, the closer it gets? And if maybe I took the limit of an infinite number of points, I would get the actual length of the curve? That's the idea of where we're going. More and more and more points. The ones off to the side are the same idea. If I'm trying to find the distance, or excuse me, the length of this curve from P0 to P1, I want to know how long it is. I could just use this distance, but that's obviously not the same. But I could break it up into 2 pieces and do this one plus that one. Make them straight so you can see them. That's closer already. See the idea now? And if I did 3 pieces, this plus this, my red's dying, better switch colors, is even closer. And the more we do, obviously, closer it's going to get. Okay, so let's derive our formula. And I'm going to use the picture at the very top right here to come up with our formula. So let's call the 2 points P0 and P1. Your picture off to your right uses PI and PI plus 1, because even if you're on the 75th one, you talk about the 75th and then the 76th point. But in general, we're starting at the 0th point. So I'm going to label these 2 points as just some generic points, maybe x0, y0, and x1, y1. Just 2 generic points up there. Could you find me the length of this dashed line? You know how to find the length of that dashed line right there?
Slope formula?
Not quite the slope formula. You're close though. The distance formula. We want to know the distance between them. The distance formula is actually the Pythagorean Theorem. Let me draw it over here to the side again. We actually did it right there. x0, y0, x1, y1. This point right here is x1, but it still has the same y0, so I lost my one. Has the same y as this guy, but the same x as that guy. How far is this piece? What's the length of that piece right there?
X1 minus X2.
x1 minus x0? That's what we were doing on my picture over there a little bit ago. We were being careful subtracting. This is x1 minus x2. How long is that piece? y1 minus, oops, I got y2, sorry, I meant y0. I said 2, I agreed with you. I have no 2's in this picture. Now, if we did Pythagorean Theorem, let's call this L. L equals, or excuse me, L squared equals x1 minus x0 squared plus y1 minus y0 squared. Take the square root. And this is the distance formula that people always tell me they don't remember. I would claim that I don't have it memorized, but I do. But really, what is the distance formula? It's the Pythagorean Theorem. Just a generic form of the Pythagorean Theorem. That's how I remember it. So if I have these generic points right here, I can get to here. That's the length of this red piece right here, which is our approximation until I get them closer together. Agreed? Okay, so now I'm going to take that. I think I'll bring it over here. I'm going to take that and I'm going to add up all of our pieces. So I'm going to have x1 minus x0 squared and y1 minus y0 squared. That might be just the length of this piece right here. This little short guy right here. Plus, I got to add the next one. I'm not going to do too many more of those. Maybe it'll be x2 minus x1, because I'll go over to a third point. Right, if this is x0, y0, this is x1, y1, this is x2, y2. I'm running out of room, sorry. You get the idea though? So the next one would be this. Dot, 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 dot. I would keep going forever, however many pieces I was adding up. And if I make those points closer and closer together, how many pieces am I going to have? An infinite number, right? So we're clearly going to need to take a limit here pretty soon. Okay, so before we do that then, let's clean this up a little bit. What does x1 minus x0 represent in words?
Change in x.
A change in x. I'm going to write that as a delta x, a change in x. However much x changes, that change in x is going to get squared. And this one is a change in y. And then the same thing would happen if I kept going, right? A change in x and a change in y and a change in x and a change in y. And I could say I want to add all those up. But if we're going to do an infinite number of them and add them all up, what symbol do we use in calculus when we're adding up an infinite number of things? Yeah, the summation notation is if it's a finite number, right? We're adding all these up. But once we do a limit, it's an integral. So this limit is going to be an integral of, and once I take the limit, delta x now becomes dx. And delta y becomes dy. That's our notation from Calc 1 when we're taking the limit as x approaches, or excuse me, the number of rectangles approached infinity if you were doing areas and so forth. What do you think the bounds are in this case? Should there be bounds? Like maybe I'm starting here and I'm stopping here. So it would just be from A to B. Those are my x's start at A and go to B. That one over here that we did to start would be from 1 to 4, if we were setting this one up. This one would have been from 0 to 5, right? Because it was 0 and then 5 for the x value. That's just a bound. You can have that. Okay, but that's weird to have a dx and a dy in the middle of the problem. So we need to clean it up some more. brackets here. So say you have some function, y equals f of x. What is dy? What do we mean by dy when we're working with
F prime?
f prime of x? F prime of x dx. Those of you who have been getting on your case about not forgetting your dx's, it matters here. F prime of x dx is dy, it's called a differential. You learned that before? So I'm going to replace this in my formula. Maybe I'll just come straight across here, so I have a little bit of room. I'm going to use that and replace dy with exactly that. So now I have the integral from a to b. I still have dx, the quantity squared, but now I have f prime of x dx, the quantity squared. I replaced my dy with what dy equals. We're almost there. Using your fabulous algebra skills, what could simplify here? Something can factor out, take the square root of it maybe. The dx. See how there's a dx squared in each term? Let's factor that out. I'll factor it out first and then pull it all the way out. If I take the dx squared out, what will be left inside here?
1 plus f prime of x
1 plus f prime of x
squared.
squared. I'm going to put brackets around that because there's so many parentheses in here. If I factor out the dx squared from here and from here, I'm left with just the 1 here and the f prime squared from here. What's the square root of dx squared?
Yeah.
Dx. So we can pull it all the way out. I'm going to write this at the top of this board over here, so hopefully I won't erase it as we work on it today. So I now have L equals the integral from a to b of the square root of 1 plus the derivative squared of the dx out here. That's what you should have somewhere near the bottom of your page. For the formula for an arc length. So this formula right here is all we need. We call it the arc length formula. It says that as long as you know your function, I can't tell it's moving my way. As long as you know your function and you can take its derivative, you can find the length of any curve by using this formula, which we're going to do. Questions on that? So before we do an example, I'm going to do a similarly. You know how when we did areas, we could do, top minus bottom if we wanted to do it, everything in terms of x, and we could think of everything in terms of dx, but we also could do right minus left if we were doing in terms of y and we did dy's. The same thing is true for arc length. Sometimes it's easier to work with your functions in terms of x, and the only thing that changes are your bounds, because these would now be y values, whatever they might be. What do you think happens inside there? What do you think changes if I'm changing x's to y's? What did you say, Joseph?
Oh, I see now.
Okay, that's good. What do you think changes? Anything? F of y? Except I'm not going to use f, and I'll show you why in a second. It's actually, I'm going to use g prime of y squared. Let me show you what I mean. Say y equals x squared. Well, let's say x cubed. There's your function. So f of x equals x cubed, right? If you solve that for x, though, what's x? X equals cube root of y. So that'd be g of y. So the reason I don't use y, I don't use f, is the f and the g functions are different. But it's whatever function you have in terms of x or in terms of y. And it's up to you which way it works better. You could do it either way. That's just a little example of what that notation means. So we can do it either way, in terms of x or in terms of y. When we start working in 8.2, when we're finding surface areas, it turns out that one way is almost always easier than the other, and it doesn't hurt to set them up both ways to see which integral is nicer. Okay, so we spent all that time deriving this equation. Let's use it. So on page 64, there's an arc length question. It says, for example 1, compute the length of, find the length of this curve on the interval from 1 to 2. So there's some messy curve. It's definitely not a line or a circle, so I wouldn't have a shortcut way to find it. I want to find the length of the curve. What do you think I need? I need an integral. What goes in my integral? Yeah, the derivative needs to go in there, so I should probably find the derivative first so I can plug it in there. So let's find f prime of x. So f prime of x is y prime. Be careful here, it might help to rewrite it first. This is 1/16 x to the 4th. You want to get in the habit of pulling these constants out front, otherwise people think they need a quotient rule when you don't. And this is 1/2 x to the -2, right? I'm just rewriting y to make it easier to find the derivative. You guys see that? So the derivative is 1/16 times 4x cubed. Okay, bringing down the 4, exactly 1. Plus 1/2 times -2 x to the -3. Carefully doing my derivatives. Fair warning, these problems get a little messy, but they work out nicely in the long run. So my derivative is 1/4 x cubed minus 1 over x cubed. With the 2 and the -2 reduced there. We good? What do I need to do with that? I need to plug it in the equation. And in the equation it's going to be squared. So I'm actually going to square it even before I plug it in, just so it doesn't get all messy yet. So I'm going to now find the derivative squared. I have to square it. Which means I have to take this mess and multiply it by itself. We can do that. For those of you who don't know the shortcut, you can write it out this way, multiply it out by itself. Bless you. Squaring it means multiplying that binomial by itself. Multiplying all the terms, you end up with 1/16 x to the 6th. Let's see what happens in the middle term. Minus 1/2. I'll talk about where that comes from in a second. Plus 1 over x to the 6th. Someone tell me where that 1/2 came from? I skipped some steps. Yeah.
Because you have the 1 over x cubed times 1/4 x cubed. So the x cubes cancel out, and 2 of the 1/4 is in the middle.
Beautiful. So when I multiply these two, do you agree that the x cubes are going to reduce? I'm just left with 1/4. So I have a minus 1/4 here. I have another minus 1/4 out here. So 1/4 and 1/4, 1/2. They're both negative. If you've done all the algebra, you'd catch up to that too. So that's the derivative squared. This is all just organization so I can figure out the arc length. There's my derivative squared. Okay, now I'm gonna find the arc length. Since everything's in terms of x, we'll go ahead and leave it in terms of x. The x interval was from 1 to 2. I have 1 plus my derivative squared, which was this guy that we just found. So I'm gonna put that whole thing in there. 1/16 x to the 6 minus 1/2 plus 1 over x to the 6 dx. It's getting messy, I agree. If I combine my terms, I now have 1/16 x to the 6 plus 1/2 plus 1 over x to the 6. You see where that plus 1/2 came from? I have positive 1 minus 1/2. Now usually right about here, I'm waiting for you guys to catch up. Right about here is where people think they're stuck. I don't know how to integrate that, that's a mess. Do I do a trig sub? What do I do, right? There will almost always be a nice way to either simplify or maybe a nice u sub. Sometimes you'll end up with a trig sub problem. This one by itself, if you asked me to look at this and simplify, I could probably get there. But let's think about why this should look kind of familiar. This should look kind of familiar compared to something we just did a little bit ago. What's it look like? Almost identical to something we know. Compare it to this. How's it different?
This is square root.
I meant just the inside part, you're right, there's a square root, that's different. So I'm talking, my question is, this part inside the square root, just this portion?
So one has a positive 1/2 and the other one is a negative 1/2.
Yeah, this one has a plus 1/2, this one has a minus, is that what you were gonna say, Evelyn?
Yeah.
So this, remember, this expression here with the negative 1/2 came from this perfect square with a minus right here. So now it looks like we have the same idea, just a perfect square with a plus 1/2. So you have to look for the similarity between here, that plus 1/2, just changes this sign here, which means it's actually a perfect square with a plus. So I am going to rewrite that as the square root of 1/4 x cubed plus 1 over x cubed squared dx. Working myself into the corner here. It's very rare that you're going to get one that doesn't look familiar to something you've done before in the same problem. Sometimes you do have a perfect square, you just kind of have to play around with it to figure out it's a perfect square. Other times, like I said, it'll be a trig sub or a u sub. Why does that help me?
Because square roots cancel out.
Yeah, the square root and the square are going to get rid of each other. We've just simplified this tremendously. I'm going to go up to the top of the board from here, see if I can finish it in this one little corner here. So the arc length now is the integral from 1 to 2 of 1/4 x cubed plus, I'm going to write this as x to the negative 3 to make it easier to integrate on myself. The squared and the square root are gone. I just rewrote it with a negative exponent. I think we can integrate that. I hope we can. So that is 1/4 times x to the 4th over 4 plus x to the negative 2 over negative 2. all evaluated from 1 to 2. Now you'll know why there's only 2 examples of this in these notes, because they take a while. I'll simplify a little bit and then evaluate. Let's see, that's x to the 4th over 16 minus 1 over 2x squared. Evaluated from 1 to 2. You'll notice that I do that a lot, where I switch from fractions to negative exponents and I go back to fractions. I only like the negative exponents when I'm integrating or taking derivatives. When I'm evaluating, the fractions are easier for me to see, but whichever way works for you, it's fine. So let's plug stuff in. 2 to the 4th over 16 minus 1 over 2 times 2 squared. Oops, my minus got minus 1 to the 4th over 16 minus 1 over 2 times 1 squared. Over 16 minus 1 over 8, 1 over 16, 1 over 2. Now I'm just going to get a common denominator of 16 for everything, the easiest way to get to my answer. So I'll multiply this guy by 2 over 2, multiply this one by 8 over 8. I'm going to barely make it. So I have 16 minus 2 minus 1 plus 8 minus the negative, right? All over 16. I didn't hear what you said, Joseph. Talking out loud again? 21? 21 over 16. 1 and 5/16 is how long that little piece of the curve is.
So in this case, while you accept mixed numbers, they're not fractions and everything.
Fraction. I mean, this would even would be a decimal that stopped if you want to put
But
it
you'd
in
be
a
okay with the
decimal.
decimal point.
Right, decimals that terminate, no problem, those are equivalent to fractions. But when they go on forever and you're rounding, all of a sudden then you've got an approximation.
Yeah.
I also recommend making sure your answer makes sense. And what I mean by that is, we're integrating from 1 to 2 on the x-axis. So I don't even have that graph in front of me, but I'm going from 1 to 2. So whatever this graph looks like, you know, maybe it's a little piece here. How long could this possibly be? It helps to figure out, okay, what's the y value that goes with 1, and what's the y value that goes with 2, and to give an estimate of how long that piece is. But you can tell, I mean, this is like a little bit more than 1, it kind of makes sense. If this distance is 1, that's a little bit more than 1. If my answer had been 75, I would have been a little worried. Because this is not anywhere near 75 in terms of the distances here. So it kind of helps to have a little visual of the graph to make sure that the answer makes sense. That was a lot. Questions, comments, complaints? Yes?
So when you had 1 plus all that, and then below you got rid of the 1, because I guess the square root of 1 is 1.
No, I added these like terms.
Oh, okay.
Yeah, you can't take the square root of
That's
each
what I
term
thought,
ever. No,
yeah.
I just added these to get like terms.
Okay.
Positive 1 minus 1/2. Yes?
If you have something like an asymptote in your bounds, would it just come out as indeterminate, or?
So you mean, let me make sure I understand what you're asking. In your bounds. So if I was talking about, say, maybe this function, going from -1 to +1,
Yep.
something like that. So you wouldn't actually be able to find that arc length. You could actually just say already that the arc length is infinite because this piece goes down here infinitely, and this piece goes up here infinitely. So arc length is infinite, it diverges. So So you wouldn't actually even be asked to find that, because that asymptote makes this infinitely long.
Oh,
Never mind?
yeah.
Okay. Yeah, just this piece is infinitely long, heck with another infinitely long piece, doubly infinitely long. Other questions, comments? These are good. Should we try another one? Yeah, why not? It'll be fun. Okay, example 2. It's a little bit nicer function at least. Example 2 says find the arc length y equals x to the 3 halves from 1 to 9. So let's write that up here. Okay. Y equals x to the 3 halves, x equals 1 to x equals 9. Want to find the length of that curve. What should I do first?
Find the derivative of y.
Find the derivative of y. Just we need to plug it into our formula. 3 halves x to the 1 half. What am I going to do with that? Square it, because it does in my formula squared, so I might as well square it here. What happens when I square that derivative? What's 3 halves squared?
9/4.
9/4, okay. What's x to the 1 half squared? It's just x, right? This is like the square root. If you raise it to the second power, the 1 half and the 2 will reduce. It's just x.
And that's simplified.
That's pretty. That's pretty than another problem. Yes,
Will we simplify the 9/4 to be 3/2?
it's not, does it reduce to 3/2? Because that's not,
Yeah, that's not.
yeah. You're taking the square root of it, so you have to leave it like that, 9/4 x. Okay, so I think I have everything I need to find the arc length. The integral from 1 to 9, 1 plus the derivative squared, that's 9/4 x. Much nicer integral than that last one we had. How am I going to evaluate that? I don't even need a trig sub. A u sub. If this had been squared, I would have probably needed a trig sub. Because it's not squared though, it's a nice little u sub problem. If u equals 1 plus 9/4 x, du equals 9/4 dx. So I can convert that. That's the square root of u. Dx is equal to 4/9 du. Right, replacing my dx. And I need to change my bounds because these are x values. This is an x and this is an x. If x equals 1, u equals 1 plus 9/4, or 13/4. And if x equals 9, u equals 1 plus 81/4, 85/4. Just converting my values here so we can finish this problem. Where'd it go? 13/4 and 85/4. Okay, let's clean it up a little bit more. I'm going to pull the 4/9 out front. I'm going to leave my messy fractions here for the moment. This is just a u to the 1/2 to u. Put my 4/9 out front. Okay, are we ready to integrate? What's the integral of u to the 1/2? Two-thirds u to the 3/2? And then that gets evaluated from 13/4 to 85/4. That's 8/27. Fractions just keep getting uglier. 8/27 times 85/4 to the 3/2 minus 13/4 to the 3/2. What does the 3/2 exponent tell us to do? Three-halves tells you to do what?
Cube root.
Not cube root.
It's a square root of cube.
A square root and then a cube. Or you could cube it and then square root it, but I like to do it the denominator first. Take the square root and then cube it. Well, 85 is not a perfect square, so I'm kind of stuck with that. And the same with the 13. But these 4s, I can do. Can you take the square root of 4 and then cube it? Yeah, it comes out really nice, actually. 8/27. The numerator I'm kind of stuck with. The denominator, we take the square root of 4, which is 2, and then cube it. So I get 8. And same thing over here. Over 8. So what's going to happen? What'd you say? I mean, not much, I could subtract, I suppose, but something else is going to happen nicely.
Well, the eight's gonna
The 8s are all going to reduce, right? This 8's going to reduce with both of those. So I'm left with 1/27 times 85 to the 3/2 minus 13 to the 3/2. Now, if you leave your answer like this, I will accept it. If you go to check the answer on my answer sheet, if this was a lab assignment question, it would look like this. 1/27 times 85 square root of 85 minus 13 square root of 13. How is that the same?
Oh, because you cubed it, so you can just pull out 85, and then you can still have the square root of 85.
Right, because it's the square root cubed, right? It's the same thing. So the square root squared just gives you an 85, and then there's one extra. So there's 2 square roots, and there's your third one. Yes?
This doesn't have to do with the answer, but when it said 85/4 to the 3/2, I also thought that it was the cube root. So, what would actually mean the cube root?
A 1/3 exponent. Like if it was 85 to the 1/3,
That's
the
cube root.
denominator tells you what kind of root it is. So the denominator always tells you your root, and your numerator always tells you your power. So you always look at the, like if it was an exponent, say of 85/4, that was your exponent, that means a 4th root, and then raise it to the 85. Good questions. Messy? You will be asked for your exact answers when you're doing these, so I know you could approximate it with a decimal. So we're going to give you exact answers. Okay, let's go ahead and take a break from here. We'll come back and talk about setting this one up in terms of y instead of x, and then we'll move on to the surface areas, which uses the same concept. We'll take a good 10-minute break from here. Before we move on to 8.2, which is on surface area, I want to show you what happens when you switch the bounds in terms of doing everything in terms of x or doing it in terms of y. and it's not always obvious which way you want to do the problem. So this problem that we just did, example 2, was this one here. Y equals x to the 3 halves, x was between 1 and 9. I drew a little rough sketch of what that graph looks like. It goes through the point 1, 1, and through the point 9, 27. If you put 9 in there, take the square root and then cube it, it looks something like this, rough sketch. How would I have set this up if I wanted to do it in terms of dy's instead of in terms of dx's? That's my question. What if I wanted to set my arc length up and have a dy on the end? That's the question. And I know the answer should be this either way. Sorry, somebody said something.
Oh, I was just thinking.
You want to share what you were thinking? No.
Sure. I mean, it would just be that second equation. So 1 plus the derivative of the function of g, which is going to be like the derivative of x.
The derivative of x. So I would have to first solve for x, so we would know what the function is in terms of y, then take its derivative, and then use the second formula here. She's totally right. So let's do that first. With your hand again?
Oh, yeah, I was saying, would you have to change the bounds to minus 2?
Yes, the bounds will have to be y's too, exactly. So the bounds will definitely not be 1 and 9. Let's talk about the bounds right now. If we're talking about bounds for y's, what are my bounds for the y's? 1 and 27. So we can do that right now. 1 and 27, because it starts at 1, goes up to 27, based on what we know about this graph. But we also have to solve for x. If y equals x to the 3 halves, x equals
2/3.
y to the 2/3. So then x prime would be my g prime of y. What's the derivative of this? It's the same example that we were doing before.
2/3 y,
Two-
negative 1/3.
Beautiful. 2/3 y to the negative 1/3. Your brain is in antiderivative mode. You have to be able to go back and forth. And then what am I going to want to do with that?
Square.
I'm going to want to square it. So the derivative squared is going to equal
Maybe 4, 9.
4 ninths.
1 over 9.
Y to the negative 2/3 or 1 over y to the 2/3. So we're just squaring it, right? Multiplying that exponent by 2. Well, that's messy. Let's put it in here anyhow. So then our bounds are y values. We're going to have 1 plus that derivative squared, 4 ninths y to the negative 2/3. And then we have our integral set up properly. Questions on setting it up? Okay, so my question now is, how do we integrate that? What technique should we try? What'd you say? We could try u sub. What would you let u be?
I was thinking that you would be 4, 9, y.
Like this inside part, maybe? Let's try u sub. So if u equals this, du is negative 8/27 y to the negative 5/3. That's ugly. Not quite sure how I'm gonna incorporate that into here, right? See the problem? I can make that a square root of u, but then what am I gonna do with this? I have an extra y to the 5/3 in there. So the u sub doesn't work. U sub didn't work. I did try though. It's not a perfect square. I suppose we could try a trig sub, what'd you say?
So what about integration by parts?
We could try integration by parts. Even if you let that whole thing be u though, that's a messy du, right? So if you kind of go through your options, integration by parts, you'd have to let all of this be u, and it's such a mess that I can't see it's gonna get any better. Not partial fractions. Maybe, just maybe, we could be creative with a trig sub, but I think that's a nightmare too. So I'm pretty stuck with this too. I mean, I don't know how I'd integrate it either. I could probably get there with some time and a pencil and lots of erasers, but I could get there. But my point is, this problem, actually in our notes, was originally given to us this way. It was given to us as, here's this function on the y equals 1 to y equals 27, right? Oh, not that function, sorry, this function, I lied, the x function. Here's this function going from 1 to 27, find the length of the curve. So if I had given you the problem in this format, you would have done exactly this. You would have taken the derivative, you would have set it up here, and then went, oh, great, now what? If it doesn't work nicely, you end up with an integral that you can't integrate, that's a big hint to switch back and just do it in terms of x's. So in this case, we already had done the x problem and it worked out nicely. But if you set it up and it's a mess, always switch and do the other one. Sometimes it helps just to write both integrals and decide which one's easier to integrate. Because I don't like this one either. I would just say, forget this. I'm now going to change it back into y's and use my x's and see if it works out better, which we just did. Everyone understand my point? You don't know which one's going to work. Just because it's in terms of x or in terms of y, that doesn't mean it's going to give you a nice integral. You might have to switch it to give you a better integral. I'm sure the lab has a couple like that. All right, so let's talk a little bit about arc length. Arc length, excuse me, we just did arc length. About surface area. So I'm flipping over to section 8.2. Surface area. Surface area, this doesn't make sense. Only for solids of revolution. I like to start this now to remind you what will be on our test coming up. We did volumes for solids of revolution, where you take some region and rotate it about an axis, or some other region and rotate it about a line. And we had the shell method, and the disk method, and the washer method, and all that. Well, now we don't want to know the volume of those, we want to know the surface area. So, you might rotate something around that ends up looking, like this, once you rotate it. Before we were finding the volume of it, like how much water could it hold. Well, now we're going to talk about how much paint you paint the outside. Surface area. Okay? And it comes directly from what we did with arc length and what we know about these solids of revolution. So you have a whole bunch of pictures on your page there, but I want to just talk about, in general, a little piece of each one. Your pictures are nicer than mine again. But imagine I have, all these little pieces here. Oops, let me put my curve in first. Same idea as what we just did. I've got some curve here, and we're going to take this straight piece here and this straight piece here, all of these little straight pieces, and approximate that curve the same way we did before. And then each of those little pieces, we're going to rotate around, say, the x-axis. So if we were rotating this whole thing around the x-axis, we're going to take each little piece around this x-axis, and we're going to get these little strips, which I've drawn on your paper much nicer. I'm going to just draw one of them, because if I try to draw them all at once, I can't. I am not that good of an artist. But the idea is that we're going to take just one of them, say this one right here, there's one right there, and we're going to rotate that around the x-axis. Around the x-axis. So when I rotate it, try to be an artist here. I can almost do this one. I end up with, I don't need to have it dashed lines in the back. There we go. You can almost see that. I end up with like this little, there's another weird thing right here though. go. It's like a little strip of paper, like a loop of this. Now it's too hard for me to get skinnier. It's like one of these, right? One of these, except it's kind of like at an angle a little bit. It's just not totally flat. It's like a little strip of paper, just that little outside part. You agree with that? So if I unfolded this, it would look maybe something like this. Right, if I unfolded it? Not unfolded, if I unrolled it. It's rolled right now. Okay, that we're looking at there? So the idea is, we're going to take this little strip and find its area. And then we're going to add it to the little strip we get from this guy, and add all those little strips up. Okay with the visual? Okay, now that I folded my paper, I want to use my notes still. Okay, so this little strip here, this piece right here along the curve, say this piece right here, whatever it might be, has some arc length that we know how to find, right? We know how to find the length of that curve. And what our book calls that notation, it calls it ds. ds is a small change in arc length. Essentially what it is, where's my formula? Oh, right here. It's this part before you integrate, just some small little change, this part right here. Each little piece, and we add a bunch of them up. A small change in arc length. There's actually even a formula, I'm going to write it over here. By me giving it those words, you'll see where this comes from now. This is your formula for ds. That's a small piece of your arc length, right? One of the many pieces that we're adding up. Or 1 plus g prime of y squared dy. So when they talk about ds, it's just they change the variables on you. They call it L in the previous section for the length of the whole curve, but each little piece that you're adding up is a small change and they call it ds. So the length here, on this piece right here, this length right here is ds. Where's the ds in this picture after I unrolled that? Yeah, it's one of these little sides right here. This side is ds, this is ds. So the area of this piece, now if ds was short enough, this would look pretty close to rectangular, right, if ds was really short. What's the area of a rectangle? Rectangle, means a triangle. Length times width. Right, so if we knew how long this was, we could find the area here. Well, how long it is, how long this is, just remember I unrolled this piece right here. It's the distance around this circle. Agreed? Distance around the circle is how long this piece is. What's the distance around the circle? 2 pi r. 2 pi r. So what's the area of that piece if it's pretty close to rectangular? 2 pi r times ds. 2 pi r times ds is the area of just this little strip. But we want to take the area of the strip we get from this piece, plus that piece, plus that piece, plus that piece, plus that one. If we let them get infinitely small, so we have infinitely many of them, so what do I need to do? Take an integral. So the surface area is going to be something that looks like that. Now here's a generic formula for it, because the r depends on where you're rotating. Are you rotating about the x-axis or the y-axis, or x equals negative 17, or whatever. So that's what the generic formula looks like. So at the very bottom of the page, I'm talking about two things. One is if we rotate about the x-axis. I have this. S equals the integral of 2 pi y ds. That over there. Where'd the y come from?
Oh, because
Yeah, why is the radius y?
Because you're rotating about the x.
Yeah, because we're talking about the distance to the x-axis, right? So if we have this strip here, this right here is my radius. Right, that's the radius of that circle. And the distance from the x-axis up to some point, that's just some y value. So I essentially just wrote the same thing again, but I put y in there. That only works if you're rotating about the x-axis. If we're rotating about the y-axis, the only thing that changes is the radius is now x ds. And we're okay with that part? That's a little review from what we did way back when in chapter 6. Test coming up on chapter 6. Now here's the part that's tricky with this section. Just because there's a y in here does not mean it has to be in terms of y, like you don't have to have a dy. And just because there's an x doesn't mean it has to be a dx. You can use whichever one you want, because remember ds could be either one. Either one, and we'll talk about how to change them as we go through some of these examples. We're going to do some today and we're going to do some next time. Because they're messy. The integrals actually turned out nicer with surface area than they did with arc length, I have to say. Okay, so let's leave that there. And let's look at my first example. I have the surface area, example 1. Example 1, surface area of this function on this interval rotating about the x-axis. We want to find the surface area. And my first question is, what does this even look like?
Half a circle.
I couldn't hear you.
Half a circle.
Half a circle. You're starting to recognize circles. I like that. Because if y equals 9 minus x squared, excuse me, the square root of that, what's y squared? 9 minus x squared, which means x squared plus y squared equals 9. So she's recognizing that it's a circle. Why is it only half a circle? Because they only have positive y values here. If there was a negative in front, it would be the bottom half of the circle. So a visual is, here's my circle from -3 to 3, because my radius is 3. But I don't want the whole circle. What do I want? Not necessarily half.
Just the 1/4 of the circle.
What'd you say?
Just the 1/4 of the circle.
I don't even know if I want 1/4 of the circle. Ah, -2 to 2. -2 to 2. I only want this piece that starts here and goes over to here. This right here is my cutoff point. And I'm going to rotate it about the x-axis. So this little thing is going to rotate it out and around. This part doesn't even matter anymore. It's not even there. What's it going to look like when I rotate it? I'm going to rotate that around the x-axis.
That's kind of
Like a what?
puck.
Puck. Oh, I like that idea. Like a puck. A hockey puck? I don't know if I've ever played hockey in my life. Actually, I used to on roller skates back in the 70s. Outside in the street, I did. Forgot about that. Just came back to me 40 years later. A puck. What else, what's another way to describe it? Cheese, oh yeah, like a block of cheese, that's a good one too. You know, you guys all know I'm not an artist, right? But it's got this flat piece, and it's a little bit rounded on the sides, and then it's flat again. Something like that. I'm such an artist. That actually looks like a hunk of cheese or a hockey puck, kind of. We agree it looks something like that? Okay, we want to know the surface area around the outside of it. Great. What do I need to do? What do I need to do? Define the surface area.
Since it's rotated about the x-axis, use that.
Beautiful. Since it's rotated about the x-axis, he wants me to use this formula right here. Agreed? Okay. So the surface area is 2 pi y ds. So I need to decide if I'm using dx's or dy's. Definitely dx's because they gave me my bounds in x's. It's not a function the other way. So if I want to do dx's, I'm going to replace ds and the y, the next step, with the formula that we have for ds that has x's in it. So I have the integral of 2 pi y, and I'm going to take the square root of 1 plus my derivative in terms of x squared dx. I'll put those on right now. So I chose to do x's because this was given to me in terms of x's. This is a function in terms of x's. And the bounds for our x's are -2 to 2. So this ds is this giant thing at the end here, the square root of the dx. What's the problem now? Chad said it a second ago.
You gotta change the one.
Yeah, there's a y in here, but I'm integrating with respect to x. I can't leave a y in there. But we know that y equals this. So we have to put that in there. The whole thing goes in there. So now my surface area equals the integral from -2 to 2, 2 pi, times the square root of 1 plus, stop it, times the square root of 9 minus x squared. I'm like, what was y? Sorry, putting y in there. Times the square root of 1 plus, what do I need to put there? The derivative of y squared. I need to find that. So I haven't found it yet. And then I'll have a dx on the end. So I need to find the derivative of y so I can square it. So we're combining what we did with arc length with our surface area. So let's come back over here, find the derivative. Carefully. We all remember the chain rule. This is my y. So y prime equals 1/2 times 9 minus x squared to the -1/2
Times negative.
times the -2x. The 2's will reduce. So I'm left with a -x over the square root of 9 minus x squared. That -1/2 came the denominator. And then I have to square all of that because my formula wants the derivative squared. So my derivative squared is x squared over 9 minus x squared. Did I hear you said?
Partial factors.
I don't know yet until I plug it in. We'll find out. He was thinking partial fractions. Once I simplify, I'll know whether or not it's going to help me. Okay with my derivative squared? I'm putting that in over here. X squared over 9 minus x squared. questions on any piece of that? Yes?
How come you put the integral sign equal to the calculus? That's an S.
Because I meant to write an S, and I turned it into an integral sign by mistake. The integral sign should have been here, but see that knows about me being sloppy. Take the points off. There you go, my S and my integral all ran together. Yes?
So in the work, I'm trying to make sure that we do this because the way you did it here, you have y prime up in the equation, but you actually substituted for y prime. So if we just did y prime, like, for me it's easy to write y prime than f prime of x.
You can call, yeah, so he's asking, can you write y prime here instead of f prime of x? So yeah, you can write it, as long as you know it's in terms of x, yes. Although, yeah, so f prime of x is the same as y prime. I'll take either one in the formula.
I just want to make sure because it's switched up.
And to me, they mean the same thing, so I don't even notice when I switch. So.
I just want to make sure.
Yeah, you can write them either way. Okay, so here's the fair warning. Most of you will get to here and panic and go, oh my gosh, this is a nightmare, it's a mess, I don't know what to do. Spend some time with your friend algebra and simplify it, and then you might know what to do. It might look messy, but we can spend some time cleaning it up algebraically, and then it probably won't be so bad. Most of our surface area ones actually clean up very nicely. So let's do some algebra on it. What should I do? Clean it up, if anything. I can move the 2 pi out front. What about in here? How do I add these? I need to get a common denominator. We can do that. I know you don't want to, but it's okay, we can do it. 9 minus x squared or 9 minus x squared. Squeeze them in there so I can combine those. I'll take your 2 pi out front also at the same time. So negative 2 to 2. I have the square root of 9 minus x squared. And I have the square root of, when I combine the like terms in here, what happens? The x squareds cancel out, right? 9 minus x squared plus x squared? That's just 9. And my denominator is 9 minus x squared. Things are going to reduce nicely. So getting that common denominator actually made it pretty. And when you have the square root of a fraction, you can make that the square root of the top and the square root of the bottom separately, right? If we do that, square root of 9 is just 3, she says.
And then cancel out the.
And these completely go away. So our little bit of panic when you saw a messy integral just turned into this. 2 pi, the integral from negative 2 to 2 of 3 dx. It will always look messy when you set it up, but that doesn't mean it's going to stay messy. So I now have 6 pi, integral from negative 2 to 2 of dx. Probably the easiest integral I will give you all semester long. Everybody good up here? 6 pi times x evaluated from negative 2 to 2. Pi times 2 minus negative 2, 24 pi. Questions? A lot, huh? Questions, comments? So I'm going to leave the other ones for next time. Because it's 8.2, we're going to finish that up. not till after our exam, so it's gonna be a while, like a week from Thursday. But we'll pick up then and keep going. The main thing is, these formulas will look messy when you set them up. Spend time simplifying, and then it won't be such a mess. Or maybe a nice U sub will help, something like that. Even though these look messier, they actually work out nicer to integrate than the Arctic formula. Okay, so we're done early today. That's good news for us. If you want to hang around and ask questions, I'll be here. If not, I'll see you on Thursday.